the window with
Okay.
the main space. So
Okay.
can you see it? Yeah, I think so because I see myself.
Yes. 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 Okay.
Okay,
Great.
should I put disconnected or
Okay. Yes. Yes. You can say okay. Stay connected. Yeah.
okay,
Thank you.
perfect.
Okay. So, hello everyone. I am Dr. Ritu Kapoor, and I'm going to be the session for this chair. I'm going to be the chair for this session, and the session. Welcome to the session on release. Welcome to the session on release engineering and DevOps at ICSI 2022. Uh, Welcome to you all, and let's start with the first presentation, first paper presentation, which is a journal first paper on an empirical study on release notes patterns of popular apps in the Google Play Store. So you can please share your screen and you can start with the presentation. We have exactly 5 minutes for every presentation. We'll take up the questions towards the end, so please try to keep it concise. Thank you. Please start with the presentation, Aiden.
Hi everyone. So you can see my screen. Everything is working.
Yes.
Okay. So welcome to my talk for this journal first paper. So this is called an empirical study on release note patterns of popular apps in the Google Play Store. This is published this year at MC with me, my co-author Safwat Ing and Ahmed E. Hassan. And this work has been collaborated through Carnegie Mellon, Thompson Rivers University, and Queen's University. So to introduce the paper, so release notes are mechanism release these messages that app stores use for every release to let their users know what is updated and how to. And apps try to use this to also sell their apps and try to advertise new features. And so an example here is from a app called Duolingo. And as an example, this one release note says that this at this release they made a new language tips and they tried to tell users how to use the new feature, as well as try to attract new users from the Google Play Store to see how cool their apps are, and how their new features are going to be used. And so we wonder if developers care about these releases or if it's just a small mechanism that they fill in. And so we survey 102 developers from app development discussion sites, and we find that 67% of them frequently update their release notes. So there is still a very large chunk of people who almost never update their release notes and just use the same few messages. However, a larger amount of them, 78% of the survey developers, say that they would love to use a tool that helps them generate release notes instead of writing them themselves. 83% of the developers say that release notes can directly respond to users. And the vast majority, 90% of developers, say that release notes are important to notifying the user base about recent updates to their app. And so, although a lot of developers don't update their apps, most of them do think it is important and that they can use them to respond to users. And it would be nice if there were tools to help them write better release notes. And so, to better justify our claims and to see what is going on, we also collect data from some of the top apps, in our case, 2,232, over a period of 3 years from the Google Play Store. And so, from that data, we have 70,000 releases, 67 million user reviews, and 2.9 million developer responses to see if the responses and the reviews are good based on which types of release notes they write.
So
So
you have
from
two
our
minutes left.
2 minutes, okay. So from our data, we try to ask three questions. So the first one is that what are the release note update patterns? The second one is on the characteristics of the apps that follow certain release note patterns, if we can find any patterns. And finally, if we can find patterns, we wanted to see if apps ever change their patterns significantly. To answer these questions, our main methods are for RQ1, we measure the length and content updatability based on cosine similarity on every release note to find patterns. On all of those patterns, we build regression models to find correlation between patterns and app characteristics. And then finally, we use time series analysis on these features of release notes to see if apps change their patterns. So since we don't have too much time, I'll just briefly summarize the results. So we find 6 different patterns of release notes. So for example, some patterns are very short length and non-updatability, very low updatability. And then some are, like for example, pattern 6 have long length and only update at major releases. And we also found using our longer and more updating release notes have high perceived quality releases, usually an increase in user ratings, and overall more informative release notes by user reviews. And for RQ3, we observed that 54 of the apps in our dataset shift their release note patterns, and of those, 92% of them go from uninformative to more informative release notes. So thank you for watching this talk, and if you are interested, please check out the paper by scanning, and I welcome any questions. Thank you.
So thank you, Adan. So now let me introduce to the next talk. So the next talk is on within project defect prediction of infrastructure as code using product and process metrics. This work has been done by researchers from Tilburg University and University of Salerno. So let's now hear it from them. So you can please share your screen, Stefano, and you can start with the talk. Thank you.
Yes, thank you very much. Okay, let me start presentation mode. Okay, so I will skip with the title. You already mentioned it. Thank you very much. So the goal of this work actually was doing work similar to traditional defect prediction in the setting of within project, but for infrastructure as code. And the goal was to propose prediction model for failure-prone infrastructure as code scripts, but also investigate the role of product metrics and process metrics for their prediction, because in the context of infrastructure as code, we have different kind of source code metrics. So infrastructure as code, in a nutshell, it's just machine readable file that is to configure software-defined infrastructures to provision those infrastructure and to manage cloud applications. It has several advantages with respect to the traditional provisioning of those infrastructures. It ensures efficient and repeatable management and provisioning. It improves consistency and reduces configuration drifts. And at the same time, it reduces the time and effort that are required to provision and scale the infrastructure. However, there are some problems with infrastructure. It's not all roses. Practitioner indeed can introduce defects then when they change infrastructure. And here we are also trying to identify which kind of defects. And there is also a study in the literature by Guerriero that mentioned the needs for instruments practitioner with tools to quickly evolve and improve the infrastructure as code. And the current work now is just limited to academia. So one of the reasons of this work was also to provide a framework that could be used in practice, since it was part of a European project called Radon under the program Horizon 2020. So just to give you an idea of a buggy playbook in Ansible, this is one of the main languages used for infrastructure as code. You can see just the line 14 and 15 here, the red and the green one. So here is a very simpler bug. When the condition, when it's a condition here, is not defined, it should be replaced by empty string or a check to none. So this is very similar in concept, but as you can see, there are different ways to identify those kind of bugs because the construct of the language are, of course, different than traditional application languages. To give you an idea of how an Ansible playbook is
You have 2 minutes left.
Yeah. So an Ansible playbook, for example, just to give you context, is just is formed by plays. Every place performs a series of tasks, as you can see, and every task calls some modules, which can be similar to traditional application methods. So for every method, for every modules, we have some parameter. Like here for the module yum, we have a parameter name and states, and those kind of source code properties can help us to identify defects in this kind of language. The objective, as I said, was to propose this framework that we call the Radon framework for infrastructure as code defect prediction. It consists of 4 main components. I will be glad to discuss with you later offline if you like. One component is to collect GitHub repository, especially for Ansible, but it's also can be extendable to other languages. Then there is a repository scorer that allows us in our study to collect only relevant repository that fulfill given requirements like the number of stars, the number of commits per month, and so on and so forth. Then we have a repository miner that analyzes the history of that repository to collect the information that we need for creating the models. And in the end, we have the defect prediction itself with the different configuration about preprocessing, classification, and so on and so forth. So we have three main research questions. And the goal was to evaluate the techniques and features that this framework should rely on. The first one was about the impact of the learning techniques. So we actually collected 104 Ansible projects and run 5 different modeling techniques classifier on them. And we use Wilcoxon text rank and consistency to evaluate their difference in performance and the effect size. We identified that amongst those algorithms, random forest was the best performing with an outcrop of 93% and an MCC metric correlation coefficient of 0.8. Also, so we noticed this difference being statistically high with a large effect size. The second research question was about understanding which metrics were the best one to increase the accuracy of the models. So for the best model in research quest 1, the random forest, we trained it with different sets of metrics, like the infrastructure as code-oriented metrics, like the number of modules, the number of tasks, and so on and so forth, or other combination, process metrics from GitHub, or process metrics plus the infrastructure as code metrics, and see how those differ. We identified that in the case of infrastructure as code, the infrastructure as code metrics are the best ones. So the product metrics are better predictor than process metrics with large effect size. The last research question was about the best predictors. So we just counted how many times the specific metrics occurred among the best prediction for that model, and we applied a recursive feature elimination on using the random forest from the previous research questions. We identify again, supporting the previous research question results, that infrastructure as code metrics like number of tokens, lines of code, the number of parameters, and so on and so forth, results among the best predictors. So to conclude, the takeaway of this work is that the first one is that for structural code metrics here outperform process metrics, and although the latter is more often effective when predicting failure prone in traditional defect prediction. The main contribution is the framework that you can find online. It's open source on GitHub and provides 104 defect prediction model for Ansible and their evaluation. So you can find the full paper in the replication package online. Thank you very much.
So thank you for the great talk. Let's now proceed to the next presentation, which is on, are you working on this? Are you still working on this? An empirical study on pull request abandonment. And this is also a journal first paper, and this will be presented by the researchers from National University of Defense Technology, China. Let's have the talk and hear it from them. Yes, over to you.
Okay, thank you. Hello, everyone. Nice to meet you online. And it's my great honor to present our empirical study on pull request abandonment. Nowadays, pull request has been the primary means for open source developers to collaborate online. However, pull requests are never perfect and ready to emerge at the very beginning. So pull request submitters are usually expected to follow integrators' review comments to revise their code until integrators are happy to merge their pull requests. Unfortunately, some contributors may give up updating their code, leaving their pull requests abandoned. Such behavior with the efforts of both contributors and integrators. Therefore, we are interested to figure out the reasons about why contributors abandon their pull requests, what the impacts of pull request abandonment result in, and how integrators deal with the abandoned pull requests. Well, what's the result? To answer all these questions, we performed mixed methods empirical study. First, we manually examine the size of abandoned pull requests collected from 5 GitHub projects. And by this, we built a taxonomy of the recent impacts and coping strategies of pull request abandonment. Then we conducted surveys with GitHub users to validate and quantify our manual findings. As for the first risk question, we found 12 reasons for pull request abandonment. First, we found some pull requests were abandoned due to process issues like lack of answers from integrators, disagree with integrators' opinions. Personal issues can also lead to pull request abandonment, like lack of time and lack of interest to make more contributions. Finally, pull requests can be also abandoned because they become not required or unclaimable. As for the second risk question, we observed 7 impacts of pull request abandonment. Among them, the commonly mentioned ones include cluttering pull request list, wasting review effort. For the third risk question, we have found 6 coping strategies of pull request abandonment, and assigning a successor to ticket hour is the most popular one. Additionally, if the pull request is not such important, integrators might advertise it to the community and expected some volunteers to pick them up.
Based 2 minutes left.
Okay, thank you. Based on our findings, we proposed the suggestions to better deal with pull request abandonment. On the one hand, pull request abandonment should be avoided, for example, by maximizing automation to reduce human effort. On the other hand, once a pull request is abandoned, platforms should suggest proper successors to pick them up. That's all for my presentation. Thanks for listening.
And so the next one is on towards incremental build of software configurations. So this is from the new ideas and emerging results track. And we have the first author as George. So let's hear it from him on this presentation.
Thanks for the introduction. Okay, so hello, I'm Aaron, and today I'm going to present our paper towards incremental build of software configurations, which is a joint work with my PhD advisors, Jamel, Olivier, and Mathieu, and published at the near track of ICSI 2022. In this paper, we are considering highly configurable systems such as the Linux kernel with over 15,000 options and many combinations of these options to get configurations. And building the kernel is really a crucial task because it is the only way to get build failures from feature interactions or test the kernel and so on. And there are multiple infrastructures that build hundreds of kernel per day. It may be random configurations or a subset of fixed configurations. And if building the kernel takes about 10 minutes for for some configurations for x86, for instance, it will take a week of CPU time to build 1,000 of them. But for smaller projects that we use every day, for instance, for the Xterm terminal emulator, we have configurations too, and we have here 3 compile time options. And the workflow when building them to test is to build them from scratch. And in this paper, we present the incremental build of configurations, which is building those configurations one after another without cleaning the artifacts to let the build system reuse previous build and avoid redundant build and gain in build time. And here, for instance, we gain 2 seconds by doing so. So in our vision of incremental build, the first scenario is ordering configurations. For 3 configurations here on the left, is there an order to incrementally build them such that we have a gain in build time, or an order where we don't gain and the build system just rebuilds everything from scratch? And the second vision the second scenario of the vision is the exploration of a configuration space, like a huge configuration space like Linux's. So from our previous order, we want to generate configurations from here, for instance, from C2, generate C21 and so on, and ensure that this newly generated configurations outperforms clean build when incrementally built from their originated configuration. And here, for instance, we can build 8 configurations in 42 minutes instead of 3 in 45 minutes. We experimented we applied our experimentation on 2 systems. So the first one is x264 and the second one is the Linux kernel. For the results of an ordering, yes?
Yeah,
Okay.
2 minutes left.
Okay, yeah, thank you. For the results of x264, we generated 2 batches of 20 random configurations, and on the first batch, we didn't find any order with significant gain. However, in the second batch, we found an order where we gain up to 11% of build time. So the lesson is that we can find an optimal ordering. And for the Linux kernel, we could not find any ordering that outperformed clean build. However, we applied our second vision, which is generation on it so we extracted a dependency graph from the source files to approximate the amount of file to recompile for each configuration. And this helps us to select the options to add for each configuration, then generate them and build them incrementally and guarantee that the incremental build outperforms clean build. And with this technique, we can gain up to 66% of build time compared to clean builds. So to sum up our paper, so the contribution is first bridging incremental build with software configurations, then the vision of ordering where we can gain up to 11% of build time, but it does not apply on random configuration or huge configuration space such as Linux kernel. So we decided to add a generation. So with a clever generation from knowledge from the project, we can generate configurations to be incrementally built and gain up to 66% of build time. As a future work, we aim to automatically find the optimal ordering instead of building every pair, for instance, like we did, and how we can automatically generalize the generation of configurations. I did not talk about correctness of build systems, but we had cases where the produced binary by incremental build was not correct compared to the clean build. And finally, we would like to make significant changes in the configurations we generate while ensuring that the build is faster and still correct. Thank you.
So thank you for the talk. Now we move to the next presentation, which is from the technical track, and the name of the talk is "Change is the Only Constant." This one is from University of St. Gallen, and we have Daniel with us. So Daniel, can you please share your screen? Yeah, and you can please start with the presentation. Thank you.
Yeah, great. Yeah, thank you very much for the introduction. This is Change is the Only Constant, Dynamic Updates for Workflows, and is joint work with Pascal Weisenburger and Guido Salvaneschi at the University of St. Gallen. We are working on updating components in distributed systems. And updating the components in such distributed systems is important because you need to have updates to fix security issues or to introduce new features. Moreover, the frequency of updates heavily increased. Meanwhile, modern DevOps organizations often update their components up to multiple times a day. But the problem with updates is that they may break distributed transactions on the systems through semantic inconsistencies in new versions of the component. And while this for many web applications is no big deal because the transactions are short running and not that frequent, which means that repeating these transactions doesn't take many additional resources and doesn't introduce much delay. This is a huge issue if your transactions are long running or very frequent, because then repeating all these broken transactions takes a lot of additional resources and introduces significant delays. And workflows are exactly on that side. Workflows tend to be long running and frequently executed. Yeah, and this is exactly the problem where safe dynamic software updating comes into play. And all these works in that direction try to find out when it is safe to update a component so that we don't break the running distributed transactions, which means that we do not have to repeat any transactions because we just didn't break them in the first place. So this is an example workflow. And you can imagine that for each execution of such workflow, a token runs through it. So this is an example execution where first a hotel is booked, then a car, and eventually a flight. And this example workflow is distributed over two components. Parts of the tasks are executed on the car rental component and the other tasks on the holiday component. And with safe dynamic updating, we now want to find out or want to define when it is safe to update a component. And the state-of-the-art safe system here approach was version consistency. And we see here marked in red when it's according to version consistency safe to update the car rental component, and in blue when it is safe to update the holiday component. And all tokens of all running workflow instances must be in these areas. So for example, now it would be safe to update the car rental component. And in this example, with the third token, it wouldn't be safe anymore. And the overall idea is that we wanted to get more of these safe update intervals. And what we noticed is that not every update actually introduces a semantical significant change. We noticed that many updates just don't change anything significantly. And previous work by Kavrikov and Robillard called such updates non-essential changes. And they described them as cosmetic in nature, behavior preserving, and that they don't give any further insights. And yeah, practical examples, simple examples of such updates would be simple comment changes or just variable renamings.
So you have 2 minutes left.
Thank you. And yeah, so we took this distinction and used it for our approach, essential safety. And with essential safety, we say for updates that are essential, that introduce a change, we have the same safe update intervals as the state of the art. But for non-essential changes, we can have these additional safe update intervals, which means that we can update earlier and we can update with less disruption to workflows. We evaluated our work by simulating 106 realistic collaborative BPMN workflows, which showed that in general, safe DSU is applicable to such workflows. Then we could show that essential safety indeed significantly reduces the overhead compared to the state of the art, and that indeed the amount of non-essential changes improves the performance of our approach. Last, we had to evaluate whether indeed many updates are non-essential changes, because that's the core idea of our improved approach. And by analyzing 8 monorepos, we figured out that in these monorepos, at least 60% of the component updates are non-essential, but practically even much more. So yes, many updates are non-essential, and our approach can help here to have better safety issue performance. To sum up our contributions, we applied previous work on safe DSU, which was only for synchronous transaction models, to asynchronous workflows. We introduced an improved approach, which leverages the distinction of essential and non-essential changes, and we evaluated all of that. With that, we are at the end of my talk. All details, of course, in the paper, more details also in the longer version of this talk on YouTube. And we have an artifact as well, which should allow you to reproduce and to recover our research. Thank you very much for your attention, and I'm looking forward to questions and discussions with you.
Thank you, Daniel. So let's now move towards the last talk of this session. So this talk is from a technical track, and this is on lessons from 8 years of operational data from a continuous integration service, a case study. And we have the author with us, so you can please take over the presentation. Thank you.
Thank you. Hello, everyone. I'm Kehliya Gallaber. My talk is about an exploratory case study of Circle CI that we conducted using 8 years of operational data. So these days, many software teams are choosing to use cloud-based CI services because they take away the hassle of maintaining your own CI infrastructure in-house. Travis CI, GitHub Actions, and Circle CI are a few. There have been many prior studies on CI, for example, on benefits and challenges of using CI. Also about CI build outcomes, such as build failures and noise. And then duration of CI builds, for example, long build duration. Also about patterns and anti-patterns of CI. All of these focus on the developer perspective for the benefit of developers. But provider perspective is largely unstudied. Therefore, we focus on provider perspective and how providers can benefit. We look at three perspectives: usage of CI service over time, builds that can provide a signal to the user, such as tests passed or failed, builds that are unable to provide a signal because they were abruptly terminated. We decided to study Circle CI because it's used by over 1 million developers, used by many software teams as shown by the number of installs in the GitHub Marketplace, because it provides a robust API to access historical data over 8 years. So as the first research question, we look at usage of CI service over time. We study the growth of two indicators, that is build duration, that is the time taken by a build to run from start to finish, and then build throughput, number of builds completed in a fixed time period. Plotting median values of these two indicators showed that the values have remained stable over time. That means Circle CI was able to provide a consistent service to the average user over time. However, when we plot the 95th percentile, it showed more and more heavy users are using the service. So this raised the question, how is these heavy users are consuming the resources of the service? So by computing the Gini coefficient of two indicators, throughput and the total build time, we observed that the imbalance of resource consumption was growing over time. Heavy users were collectively using more and more resources. So to summarize, we found out as the CI provider, they were able to provide a consistent service for the regular consumers. However, resource consumption by heavy users is growing further. And in terms of signal generating builds, we found out for the average user, compiling and tests take up most of the build run time. However, if we consider heavy users, heavy user builds spend more time downloading dependencies. Then we looked at why some builds are unable to generate a signal. We found out 4 reasons: user cancellation, availability issues, configuration errors, and exceeding time limits.
You have 2 minutes left.
Okay. To address these limitations that we identified, we have some recommendations. To reduce the load on the server by the heavy users, services can implement tools proposed in prior research for build acceleration. For example, some have proposed to use machine learning techniques to skip CI builds, or selectively building based on past heuristics. Then the CI service have the choice of allocating future investments. For example, if they want to benefit the average user to make a lot of developers happy, they can choose to optimize compilation and testing stages. For that, they can use techniques such as test selection, as the one shown on this slide, that is about regression test selection. Or they can make heavy users happy by allocating more and more bandwidth for downloading dependencies, because for the heavy users, the downloading dependencies take a lot of time. So that concludes my presentation. You can find more details about the observations and lessons learned from our full paper. Thank you very much.
So thank you for the presentation. We can now take up the questions for each paper one by one. So let's start with the first paper presentation of the session, an empirical study on release notes patterns of popular apps in Google Play Store. So do we have any questions for the first paper?
Yeah, so what I wondered is many apps meanwhile roll out new versions of a software where they can have the release note in the app, but actually they use toggles, meaning that the software is already on the device, but the feature gets enabled then later on somewhere without any relation to these release notes. And is it just something that is very rare and only with big companies, or do you have any insight on how release notes and that version toggle method can somehow get together?
So Ellen answer that. Do we have this, or I think they left the talk, the session. Yeah, I suppose they've left the session. So sorry. You can maybe contact the authors. Okay. Okay. Thanks, Daniel, for the question. But unfortunately, we don't have the authors with us. So maybe you can talk with them after the session. Yeah, maybe we can take this offline. So let's come to the next paper, which is within project defect prediction of infrastructure as code using product and process matrix. So do we have some questions for this one with us to answer the queries?
Right one. So you mainly focus on configuration as code solutions, and I was wondering, would your study also would you expect similar or different results if you look more into infrastructure provisioning tools like Terraform or Pulumi? And that's the first thing. And the second thing, you wanted to extend, I think, to Tosca, which gives you a YAML-based interface. And Pulumi and AWS CDK also now support YAML. So do you see there any synergies to extend this study?
So actually, I'm not really expert in the other language that you say, Pulumi, no? But actually, I think the result may be similar. And like we are also extending in Tosca, and we did some work and we found similar results, first of all. So it's YAML based like Ansible. So of course, the construct just differs, but it's the same concept. I guess they perform similar in other languages, mainly because, at least in terms of difference between product and process metrics. So in this paper, we observed this difference, which is very high. And the assumption that we made in the paper itself is that infrastructure as code doesn't change too much or as much as traditional source code. So we may expect not to find a lot of defects by analyzing just process metrics. And yeah, also many of the languages are declarative.
Okay. But you wouldn't expect a difference between configuration as code and infrastructure provisioning code.
Well, I can't speculate on that. I don't know. So far, I can tell you that the difference between Ansible and Tosca, I mean, the similarity between Ansible and Tosca are the same in within project defect prediction, because we are working on that. But I can't speculate on other languages or paradigms.
Okay, thanks.
I think so will be pretty much similar, but that's my conjecture.
Okay, so do we have any more questions for this paper? Yeah, Kaelia.
No, I have a question for the other paper, the next one.
Okay. So let's move to the next paper then. Thank you, Stefano. Yeah, thank you. So the third paper we have, are you still working on this? An empirical study on pull requests abandonment. So do we have the authors with us? Yes. So yes, you can please speak your question.
So Michael, the relationship between bots and pull request abandonment. So a lot of pull request and open source projects these days are using these bots to check different things. Have you observed a relationship between the usage of bots or activity of bots in pull requests and they are being abandoned? Thank you.
Thanks for your question. We have when we collected this pull request, we have manual verified some, and we removed all the pull requests submitted by both. So all the pull requests we investigated were submitted by human developers. I don't know whether I answer your question correctly.
Yeah, and sometimes like bots are not only submitting pull requests, but sometimes commenting on them about checking some changes and style problems and things like that. Did you observe anything like that?
Sorry, like what?
For example, if in the project, if there are some style guidelines, and in the pull requests, if they are being violated, sometimes the bots are commenting. They are saying, "Okay, you need to fix this first," something like that. So,
Sorry, I cannot understand you clear. Can we chat it and?
sure, we can.
I will come back to you.
Yeah.
So sorry.
It's okay.
Okay.
So do we have some more questions for this work? Yes. Daniel, do you have a question? No. Okay. Thank you. Okay. Let's move to the next paper. So we have the next paper. We have towards incremental build of software configurations. So are there some questions for this one?
Guido Silvanetti, University of St. Gallen. So thanks for the very nice presentation. So I was wondering, when you try to build the incremental configuration, what do you consider as part of the configuration? I guess like the if defs in the code, for example, is what else? Is it also, for example, dependencies with other libraries that might be updated in the meantime, or different libraries that you could link depending on the configuration? So what exactly is a configuration? I guess that's my question.
Okay. So first, for the Linux kernel case, a configuration is all the options in between ifdefs preprocessing macros. And what we are considering for the generation is we built a dependence graph, because there is a kind of a feature model at a higher level of abstraction where we have all the options. But you have dependency between the options at a higher level. So it's, I don't know, maybe for a driver A, you need the driver B. And there is another kind of dependency, which is a more lower level, which is the dependency between the files, of some options. And for this work, we first tried with just options, and we found out that the dependency between the options at a higher level is not the same as dependency between the files. For instance, two options that are not really related can be implemented in the same file. And so if I change this option, I have to rebuild another option with all its dependency, even if they are not related. They're just in the same file. So we checked all the options that are in the same file, and we approximated how the change of an option can impact a file, and how this file can impact other options in their files. And then we approximate for an option modification in the configuration, how much file would be recompiled, rebuilt, or added in the dependency. And then we get the options with a few files, and we incrementally mutate the configurations and so on.
Maybe if there is time, another quick question. I found the results of the paper unexpected. So I would have expected a huge gain from this incremental like in orders of magnitude of gains from an incremental build instead of the standard one. What's your insight? Why am I colossally wrong, or?
I think there are 2 points. There is first the idea of incremental builds, incremental computation, that everyone think that it really speeds up the build, but there is also the implementation of this algorithm at the build system level. And here, I think we should dig a little bit more on the amount of read or not computation that the makefile does but should not do.
Okay.
And so it's about really the implementation, the strategy, and
because in a very naive way, I would expect, it's like I don't know, like the equivalent of processing an entire list and just adding one element to a list. Right?
Okay, so yeah, but an option may be implemented just one file, but sometimes it's scattered around the whole project. And adding just one option is, when you add just one, for instance, if you add an option for the Linux kernel at the scheduler level or something like that, it will compile a whole bunch of files. So it's just one option, but it compiles almost the whole project. So we need to select the options that do not spread the bit like this.
Thanks a lot.
Thank you.
Thank you, George. So now let's move to the next paper, which is change is the only constant. So do we have some questions on this paper? We have Daniel with us to answer the questions.
We have a question. Daniel, first of all, congratulations on your Best Artifact award. And the question is about the applicability of this for other workflow engines. So how much work is it to implement this on other BPMN workflow engines or other workflow engines?
Yeah, thank you very much. And that's a great question, and actually it's something we currently try to figure out. So what we think is the adjustment for the workflow engine itself is rather minor. So basically you need to have certain status messages that this workflow engine is sending to the orchestrator during the execution. And this extension is not that hard if you can somehow hook into the workflow engine. What is a bit more effort is to adjust the orchestrator that actually performs the updates, so that it actually takes these status messages into account. And we currently implement a prototype for that on Kubernetes, and have various insights there already that it isn't trivial. Yeah, we're close to having a prototype and want to see then also what is practically the performance impact. Yeah, but generally the insight is, I think the workflow engine adjustment is not hard. Getting it into the orchestrator is a bit more effort, but generally should be doable.
I see. Thank you. Very interesting.
So do we have some more questions for this work? So congratulations, Daniel, for the Best Artifact Award.
Thank you very much.
So, okay, then let's move to the next work. So the next paper was on lessons from 8 years of operational data from a continuous integration service. So do we have some questions for this work?
I would have one. Yeah, Kelly, I really enjoyed your paper as well. Great work. And one thing I was wondering is, so if I got it right, this entire study is based on open source projects. So you started from the BigQuery GitHub dataset, which has open source projects, and I guess that also CircleCI only has for open source stuff the data available. But from my intuitive impression, like open source projects tend to be more frameworks and libraries, while business applications tend to be no open source. And what I wonder what your insight is on whether your results you would expect to have similar for closed source, or whether you would expect additional insights and results, especially because I also expect that more continuous deployment and delivery will be in business applications than in the CI of open source applications.
Yeah, I agree that there will be differences between how like private repositories or commercial repositories are using the CI service compared to the open source ones. Um, but another aspect we need to look at is we were looking at the CI services perspective, the service providers perspective. So a number of open source projects has a larger impact on the service provider because the number is high. So we cannot really say their impact is minor. Um, but I agree with you that there are differences in how this has been used. Even in the open source projects itself, we noticed, as I explained in the results, there are some projects that are building heavily and they are taking longer build durations, and what they are doing during their CI process is different from smaller projects that are having like smaller builds or that builds that end in a shorter time. So yes, we can find interesting insights depending on all these different types of projects and what they are doing during the builds. But unfortunately, we don't have access to that type of projects, commercial ones. But I assume still from the open source sphere itself, we can find all these differences of how projects are using CI. For example, as I explained, in some cases they have steps that are heavily dependent on network, so they have to think about allocating network bandwidth. And in some cases, they might be using very high CPU or sometimes a very high disk. So depending on the project type or project what they are doing during the CI, the load on the CI service itself may be different. So yeah, so there are interesting patterns we can find there, and we can provide a lot of insights for the service provider itself. So we have shared these findings with Circle CI and hope they'll find it useful.
So you mentioned you got in contact to them. Did you get any direct feedback of them already? I'm just curious.
No, not yet.
Okay, thank you very much.
Thank you.
Thank you, Kelia. So do we have some more questions for this work? Okay. So then maybe we can take up some more extra questions from the papers of this session. Any more extra questions on any of the papers? So I have a question for the second paper, within project defect prediction of infrastructure as code using product and process metrics. So Stefano, yeah.
Yeah.
So do you, the metrics that you consider, do you also consider some metrics which actually also consider the programming style in which the code is written by a programmer? So
No,
do you also,
we just consider the property of the source code, static properties.
okay. So do you find the use of some metrics could actually help in improving this work or bring out some new insights which have not?
I think I lost there. Is it me or? Okay, sorry. Can you repeat the last part because I lost you?
Yeah. So I'm saying that do you have any comment on that using such kind of metrics? It might help in getting up some new insights of that work.
No, actually, we didn't think about that. So that could be a nice idea, actually. But yeah, definitely. Can you make me also an example of the metrics that would you like? to see, because like the results so far are really accurate for at least within project effort prediction. So perhaps I see using other metrics more for refactoring operation, or I don't know, do some developer-oriented effort prediction. But yeah, I would like to know more about the metrics that you have in mind.
Yeah, which actually like we have proposed, which have shown that there is the defects do occur. Style is the software quality does depend upon the way the programming constructs are used, the manner, the syntax in which they have been used, the style in which they are leading to different performance issues or leading to different bugs. And so
Yeah.
it does depend on the quality of the product, or the defects do occur from the programming style that a programmer uses. So in that context, I was talking about.
I agree. That will be really interesting, but at the moment I see two main challenges about that. The first one is the declarative nature of the source code, in at least for like configuration management languages like Ansible. So you can say it's pretty straightforward. So there is not a specific programming style there compared to traditional source code. And then the second challenge is that the programs that now are written which using configuration management languages are relatively new. So we were able to find 100 suitable projects, but most of them, they are new, so you don't have many commits, and that's might be a difficulty in analyzing the story, and also the specific pattern or specific developer.
Yeah, thank you. Yeah. So the papers that we discussed today in this session, or else we may wind up the session. Okay. So let's maybe close this session, and please keep it in XC session. Thank you. That's all from my part. Thank you. Have a nice day. Yeah.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.